Good afternoon, student. Again, the series of lecture series of abstract algebra. We will continue with the ring and idle because some more properties here. The principal ideal domain. We will talk about the domain, integral domain, ideal. Now today we will go through the principal ideal domain and some important theorem of ideal and rings. Okay. Again, we will know about the more properties of ring. Actually, ring and group is the wide area. So the topic is continued between the rings. So to understand the properties of ring, to know about the ring and ideal. Ring and ideals means we are very clear that this side of it is a type of solving which follow the cancellation law. So now we move on our lecture. Last video we will discuss about last video we discussed that about field. Field is f has two ideals 0 and f. So if a commutative ring is there are two things if CRU have only two ideals means 0 and f, then it is a field. We have already proved that. Second, we prove that ZP is a field if P is prime. Third, about the field that if finite order integral domain is a field. Is it? So here we need finite form. Now we move to the another theorem. Let R be a ring with unit element. Let R be a ring without with unit element. R have the unit element but need not to necessarily commutative such that the only right ideal of R are 0 and R. Prove that R is division. Now we have to show that R is has a unit element, is not the commutative law, and has only right ideal R or 0. Then we will show that R is a division ring. For so division ring, that is every non-zero element every non-zero element of R having multiple inverse. That means if an element A which is not 0 in R, A is not equal to 0, then there exists B, so A dot B is equal to 1. If we take, if possible we take A is not 0, for A belongs to R, then the set AR, AR is a right idle, right idle of, for prove this division ring, we have to show that R each element A which is not 0 have the inverse element. For that, AR and AR is the right idle of R. Let 1 belongs to R. For that, A dot 1 is equal to A belongs to A. And since A is not equal to 0, therefore the right idle AR and S R is given to be having no proper right hand. Since therefore one belongs to A. Therefore the right ideal AR is not equal to 0 and AR is equal to R as R is given to be having no proper right ideal. Since R is equal to AR, therefore A belongs to AR. 1 is equal to AB. For all B belongs to R. So B is multipli- multiplicative inverse of. Actually A belongs to R, AR, then there is just a element B. So AB always give us 1 and 1 is the identity element of multiplicative. So we can say that B is the inverse element of A. If so AB is equal to 1, B is the inverse element of A. Now, now B is multiple inverse of A. Now we will show B is also left multiple inverse also. Now B is left multiple inverse. So inverse also. Okay. So PA V we can we do this because ring is follow the associative property multiple associativity. Now AB and AB is equal to this is the right inverse. So we can say b dot 1 is equal to. Now b is also a non-zero and as such that as that b inverse is equal to 9. That show that b is also left as such that has the right multiplicative inverse such that inverse 1 b a b is equal to b a b inverse that show that b is also left multiplicative inverse of multiple inverse of a and R is division ring. If each element has the multiple inverse, so we can say this is a division ring. Now, one more theorem. Let 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 S be an ideal of ring R with unity S is equal to. Let as we consider R is a ring with unity. One and A, the unit element, then by inverse exist and belong to R. Consider R is a ring with unity 1 and A be a unit element of R, then by inverse exist and it belongs to R. Now, by definition, now A belongs to R and also A belongs to R. Then R 1 belongs to by definition of 1 belongs to S. Now we have to prove that S is equal to R. Now have to prove that let S be an idol of ring R with unity, then S is equal to R. So consider R is a ring with unity 1 and A be a unit element of R. Then by inverse exist before we already proved that is the right idol, then inverse element of its multiplicity which exists. So we can say that A inverse exists. Now we will show that S is equal to R. For this, let X be any element of R. We will show that this is also S and S element is also R. So we will can show that S is equal to R. R then X belongs to R, 1 belongs to S. That implies S, this implies X belongs to S. That means also H, S is an idol of R. So if R belongs to S and S is given to belong, that means S belongs. Actually, we have show that S is ideal of R. So S belongs to R. S is the subset of R. And we take an element from S from R and we show that this is the also element of S. So R is the subset of S. Then do by two equations. S is a subset of R and R is the subset of that thing can possible. Then S is equal to. Now writing some statement very important. You can say example. The left ideal generated by the union I1 union I1 union I2 of to left ideal is the set of consisting of the element of R obtained by adding any element of I1 any element of I2. The left ideal generated by the union of I1 union I2 of two left ideals is the set I1 plus I2 consisting of the element of R obtained by adding element of I1 to I2. That means the meaning of the sentence that left ideal always left ideal generated by the union of I1 I2 and the element of this ideal is like I1 plus I2. Clear? The statement is some complicated, but we try to understand the statement that left ideal generated by the union of I1 union I2. There are I1 and I2 two ideals of ring and left ideal generated by I1 union I2 and the element obtained in this ideal are with I1 plus I2. This type of ideal is existing. Now we have to show that the element of I1 plus I2 generated by the I1 union I2. Here let let I1 I2 R to I to I and S is equal to S is equal to I1. We have to prove to show that I1 plus I2 is ideal generated by generated by we will generated by. So first we will show first I1 plus I2 is a left hand. Second I1 plus I2 I1 meaning I2. Third if any left idea if idea contain I1 union I2 then I1 plus I2 is also true. These are the three parts we have to put I1 plus I2 is ideal. Again, let I1 I2 are two ideals. And S is the I1 union I2. We have to show that I1 plus I2 is ideal generated by I1 union I2. So first we will show that I1 plus I2 is an left ideal and I1 plus I2 is a subset of I1 union I2, and if any left ideal contain I1 union I2, then I1 plus I2 is also contained in it. So, student, this will be for your practice. Here we take the two elements of I1 plus I2. I give you hint. We take the two elements I1 plus I2. Let P A1 plus A2 and Q A1 plus B. These are the two elements of I1 plus I2, where A1 belongs to I1 and B1 belongs to I2 belongs to I2. So this type we will show that this is a field. For field, sorry field, have to ideal. For ideal we will show that this is a first this is a close. So we check I1 minus I2, P minus Q element in the I1 plus I2. Then we show that right multiple and left idol exists. So this type of we will do in next lecture. Now we come to the quiz. This is the quiz time of today. Which is the field? The quiz, the first question, which is the field? Z2 plus dot, Z4 plus dot, Z6 dot field, and all are true. So I just tell you one thing that Z2 plus dot, this means modulus of Z2. We will discuss about here Z4 modulus set, where the element Z4 element is 0, 1, 2, 3 plus 4 dot 4. Z2 element are 0, 1 plus 2 dot 2. Z6 element are 0, 1, 2, 3, 4, 5 plus 6 and Z8. So here I told you a theorem and the remark, then ZP is the field if P is a prime number. So we can easily see in this Z2 is a prime number. So Z2 is a field. Which is the two? Intersection of ideal or ideal? Union of ideal ideal, not all. So first is the right answer. Intersection of ideal always ideal. Which statement is not true? Intersection of family of ideals and ideal. Z plus P A integral domain. 2Z plus is a field which is not true. Z2, okay, not 2Z. Z2 is a field and not. So first we take intersection of family of ideals and bilkul right. Z plus Bj integral domain right. Z2 is a field right. So not. All other true. Which statement is true? Z plus is a CR is right. The union ring has not zero divisor and Q plus is a field. Not zero. All are true. These are all are true. Which statement is true? Every idol follow the constellation of बिल्कुल right. Idol is a subring. एकदम right. Every ring is an integral domain. This is not right. So this is one more than one and answer is right. This is the pattern of CSL NAT exam. Then he asked about the one more than one is the right option. So A is the right, B is the right, or C is not right. D is the right. I am putting some question from CSL NAT also that it will be helpful for you to understand the uh, picture of the exam pattern. So every idol follow the cancellation law. This is right. Every idol is a subring. Is it right? But C is the wrong and D is right. D is the right question. Thank you very much. Thank you very much, friends.